So this integral was on one of the final exams at MIT, this integral of x plus 1 over square root of x squared minus 4x dx. And in the instructions, it says, at some point, it will be useful to make an inverse substitution. It will be simplest to use an inverse hyperbolic substitution. And then they give some identities that you could use. Okay? I did not even pay attention to any of that because you do not need to use hyperbolic sine, hyperbolic cosine, any of those. You don't. And most people hate those functions. And that's okay. Because honestly, even I don't like them. And I never really used them either in my career as an engineer. I never had to come across it, actually, as of the current moment. So you only really need to know it, at least from my experience, for some classes. But as I was saying, you don't need to use hyperbolic sine or cosine for this. I solved it in a completely different way that gives me the exact same answer. It might be in a different form without hyperbolic sine or cosine in the answer, but it's totally valid as well. If you differentiate this, you actually get back that. So that's correct, right? Okay, so here's what I did. Here, I thought to complete the square so that I could maybe do a trig sub. All right, so first of all, before even that, I see that I can't do a substitution of like u is x squared minus 4x, because du would be 2x minus 4 dx. That doesn't look like that up here, or it's not even close, right? So that's why I thought maybe let me complete the square to make the bottom a little nicer, okay? So that's what happened over here. And now these first three terms, that's just the perfect square, x minus 2 squared minus 4. So then here, I made a substitution, u equals x minus 2, du is dx then, and the x plus 1, I can also substitute in terms of u. That's just u plus 3, all right? So after I make the substitution, this is what I get, okay? And then I split it out into two separate integrals because this one I can solve by another substitution. This one I can solve by a trig sub, okay? So let me go over that now. So this is the first integral over there. So let v be u squared minus 4, dv is 2u du. Substitute, you get this over here, okay? Now we use the power rule, and then we simplify and back substitute, okay? So this is square root of u squared minus 4, right there. All right, now this integral, I did a trig sub. Set up the triangle. Again, go watch my crash course on trig sub video if you don't know how to set this up. I'm not going to go over it here, but the substitution is u is 2 secant theta, du is 2 secant theta, tangent theta, d theta, and then we can substitute that square root term as well. That's just 2 tangent theta. Okay, so we substitute everything. These 2's would cancel, the tangents would cancel, you're left with secant. This you should memorize. That's ln of secant theta plus tangent theta, okay? And then we just back substitute secant theta, that's just u over 2. Tangent theta, that's just square root over 2, okay? So that's this here. Our original integral was in terms of x. This is in terms of u, so we got to back substitute once more. And that's our final answer right there. See, clearly, there's no hyperbolic trig function here. You don't need it. Okay? So this is probably the hardest integral that was on this final exam. So those of my viewers who like to criticize on how supposedly hard universities to get into keep giving easy final exams, you'll be surprised at how easy these next problems are. All right. This one. Integral 1 to 2 dt over t to the 2/3 times 1 plus t to the 2/3, okay? Here, I tried to find a substitution. Clearly, t to the 2/3 doesn't work because that'll be, the du would be like 2/3 t to the minus 1/3. That doesn't quite match that. So I thought, what about t to the 1/3 power? Because this is t to the 1/3 squared. We could rewrite it like that. So du is 1/3 t to the minus 2/3 power dt. Minus 2/3 power, we can move that to the bottom. Not a coincidence why I chose it like that. And then it's 3 du is dt over t to 2/3, okay? So this is the 3 du, and this is just 1 plus u squared. This should look very familiar. This is just arctangent, okay? Oh, by the way, this is a definite integral, so you got to change your limits of integration when t is 1, u is 1 to 1/3, which is 1. When t is 2, u is 2 to the 1/3, or cube root of 2, okay? So that's this, and then we use fundamental theorem calculus, and that's our answer. Very easy. You just have to be able to see the substitution. Maybe it takes 2 tries, and then you'll be good. Like, even in my head, I had to do 2 tries. But it was really simple. This one's very easy as well. They even gave a hint in this integral. So again, those of you viewers who like to criticize hard universities giving very easy problems, they even gave a hint that use trig identity. What is tangent squared equal to? Tangent squared is equal to secant squared minus 1. You don't even need that hint. It's really obvious, actually, if you've solved these trig integrals before. Okay? Again, that just comes from experience. So, more of the story, practice a lot, and then you won't even need those simple hints. Okay, so, by the way, before this, even any of that, you should realize the trick to this problem is it's an improper integral. Why? Well, tangent theta at theta equals pi over 2 is undefined. Remember tangent theta? There's an asymptote there. Okay, so I didn't pay attention to that, so I just solved it like any regular definite integral. So tangent squared is secant squared minus 1. All right, so then integral of tangent squared, secant squared is just tangent, integral of 1 is just theta. And then I realized that as I was doing fundamental theorem calculus, well, tangent of pi over 2, that's undefined, so this integral clearly diverges, okay? The problem didn't say it was an improper integral, so you had to pay attention to that. Okay, so that's the tricky part for this one, per se. So the proper way to do it probably is to write it as a limit, because technically, you're not allowed to do it like this, even though most people do it like this after they learn calculus. Okay, so you got to write it as a limit, and then it'll still be infinity, so divergent. Okay, otherwise, this was very simple otherwise. Okay, this one, integral from minus 2 to 0, dx over x squared plus 4x plus 8. So immediately I thought looks like a rational function, so maybe partial fraction decomposition. However, the bottom's not factorable, at least into nice integer numbers. So I couldn't do that. So then I thought, what if I complete the square? All right, so the first 3 terms are x plus 2 squared. And then I made a substitution. U is x plus 2, du is dx. We gotta switch our limits of integration though, because it's a definite integral, so it becomes when x is minus 2, u is 0. When x is 0, u is 2. So dx is just du, and the bottom is u squared plus 4. This is arctangent. Hopefully you recognize that. If you remember the general formula, it's 1 over 2, arctangent of u over 2, evaluate from 0 to 2. Fundamental theorem calculus, you get this, and then simplify pi over 8. Very easy as well. Just had to complete the square. Okay, this one's even easier. It gets easier, actually. Okay, integral from minus 10 times e to the pi to 10 e to the pi of this guy over here. Whenever there's symmetric limits, you already should be suspicious, especially weird symmetrical limits. What did you learn about? Even and odd functions. Well, if it's an odd function and you integrate from like minus a to a, it's 0. Is this an odd function? It is. Because if you do f of minus x, you get negative f of x. Therefore, integral is 0. It's a piece of cake. 2 seconds to think about this. Again, the clue was he has symmetrical weird limits. Why in the world would they do that? They're trying to trick you or intimidate you, but look how easy it is. All right, this last one. Integral from 1 to 2, x times ln x squared dx, okay? This one should be hopefully quite obvious which technique to use, or which technique could work. There's probably multiple techniques you can use. But if you paid attention in lecture, you probably went over, or in the homework problems, you probably had to do integral x ln x dx, or just integral of ln x itself. That was all integration by parts. So immediately I thought, integration by parts, let's try it. So let u be ln x squared. So du is 2 times ln x times 1 over x dx. You need to chain rule, be careful. And then dv is, sorry, you should write it like this, whatever's left. Okay. So v is half x squared. So uv minus v du, that's right here. This is integration by parts as we expected. Hopefully you've done this before, or in lecture that your instructor went over this. So set it up u is ln x, du is 1 over x dx, dv is x dx, v is half x squared. So again, uv minus v du. Okay, so that's here. Okay, now this is just simply power rule. All right, so notice how I just evaluate everything at the end from 1 to 2. This is just what I do. I don't go bother to evaluate this and then evaluate this in the middle. I just do everything at the end. Okay, and if you do fundamental theory and calculus and you simplify a little bit, you should get this. All right, so these are all the integrals that appeared in one instance of MIT's final exam for their Calculus 1 course. All right, you can see pretty straightforward, most of them. Maybe like this one's quite straightforward. Let's go over it again. This one's very straightforward. You just have to know even odd functions. This one, you had to just complete the square. Again, there's probably other ways you can solve this, but this is how I did it. This one is improper integral. That was the trick here. Otherwise, it was very easy. This one, substitution. This one's the hard one. The harder one. It was totally doable though. You didn't even have to use, again, you don't have to use hyperbolic trig functions that no one likes. Or not no one, I'm sure someone out there in the world likes it, but most people, I'll confidently say, don't like. Okay? And again, this just goes to show that if you're, again, watching this for funsies and were curious how hard an MIT final exam is, at least this one that they posted publicly on their OpenCourseware website, it's quite simple, actually. No real tricks to it. And it shouldn't be surprising. I said this in some other comment to someone who criticized UCLA's professor or whatever. Shouldn't be surprised that most of these exams are similar level, no matter what university it's at, because all the teachers want you to know the same thing. Okay? Of course, you can make it super duper hard by maybe including like 5 different techniques into one integral, but that's probably not the point of the what the teacher wants their students, what the teachers want their students to take away from the class. They want to know how to problem solve things like this, complete the square maybe as a little trick, be able to integrate by parts. Again, yeah. So that's it for this video. I'm just gonna end here now. Hopefully this was interesting to you, or if you were studying for a final exam, maybe this is a good practice set. All right, so please like and subscribe if you found this video helpful or interesting, and hopefully I see you in another video. Bye.